Hello and welcome to this calculus video. Today we will be talking about applied optimization.
Math 112.
The extreme values theorem tells us that continuous functions defined on closed bounded intervals have a global max and global min value. We also know that these values must occur at a critical point, or the endpoint of the domain. Optimization of functions has many applications to real-world problems, but in these scenarios we have to work out what the function and its domain are, and the hypotheses of the extreme value theorem might not be satisfied, so we might have to work a little harder. Let's look at an example problem. A farmer has 2,400 feet of fencing and wants to enclose a rectangular field bordering a straight river. What dimensions of the field has the largest area, given that we need no fence along the river? In order to get a feel for this problem, it's good to draw a picture. We could have a wide and shallow field, or a narrow and deep field, or something intermediate. To solve this problem, we want to re-express it in terms of finding the maximum or minimum value of a function. The problem says we are interested in the field of largest area, so a fair goal would be to maximize a function that expresses the area of the field. The field is rectangular, so its area is given by a equals base times height. We can name the sides whatever we like, but I will choose x and y because I happen to have drawn vertical and horizontal lines. So we want to maximize the function a equals x times y, but this is a function of two variables, and we only have tools to deal with one variable functions. So now we would like to eliminate one of the variables in our function. To do so, we go back to the problem statement. We see that we are allowed 2,400 feet of fence in total, and that 2,400 equals 2y plus x. Therefore, x equals 2,400 minus 2y. We can substitute this into our expression for the area, and we find that a equals y times 2,400 minus 2y, which equals 2,400y minus 2y squared. So now we have a function that we can try to maximize. Before we proceed, it's fair to consider the domain. The constraints of the problem tells us that neither x nor y can be negative. This gives us the range of values from 0 to 1,200 for y. So now we have a nice closed bounded domain to maximize our function on. To do so, we would differentiate a and find the critical points, and test these and the endpoints to see which gives the largest value for a. I'll leave computing this as an exercise for you all. Let's talk about a general outline to apply to such problems. Firstly, we should carefully read the problem, trying to identify what the unknown goal quantity is, what quantities are given, and what constraints there are. It's usually helpful to draw a diagram and identify the given and required quantities on your diagram. Then we start naming quantities with symbols, labeling our quantities on the diagram. It's good practice to give definitions of these alongside. We then try to express the quantity we want in terms of the other things we have named. If our expression has multiple variables, then we use the given information to find equations among these variables, which allows us to eliminate them until we only have one variable in our function. We then use our ideas about finding extrema to find the global maximum or minimum value, whichever our problem asks for. That's all for now, folks. Today we talked about optimizing in applied scenarios. We outlined a general procedure that you can use to apply to word problems that can be interpreted as optimizing a function.
Math 112.